Today let us learn about Diffie-Hellman Key Exchange. In secure communication, two users need to share a secret key without exposing it to others. This is where Diffie-Hellman algorithm is used. Let us understand this using Alice and Bob. Alice wants to communicate securely with Bob over a public channel where attackers may be present. Instead of directly sending the secret key, Diffie-Hellman allows them to generate the same key independently using mathematical operation. They first agree on two public values, a prime number q and a primitive root alpha. These values are known to everyone. Then Alice and Bob choose their private key secretly and generate public keys using a formula. Finally, they exchange keys and compute the same shared secret key. First, Alice and Bob share a prime number q and an integer alpha such that alpha is less than q and alpha is the primitive root of q. Then both Alice and Bob, they select a private key XA and XB such that XA and XB both are less than q. Alice then computes a public key YA using the formula YA is equal to alpha raised to XA mod q, and Bob also calculates the public key YB using the formula YB is equal to alpha raised to XB mod q. Then after generating the public key, both of them exchange these keys. Then they calculate the shared key using Z is equal to YB raised to XA mod q, and Bob calculates the shared key using the Alice public key Z is equal to YA raised to XB mod q.
Now I will explain the working of algorithm using test data when there is no man in the middle attack. The test data are alpha equal to 5, q equal to 23, Alice private key XA equal to 6 and Bob's private key XB equal to 15. Now Alice and Bob will calculate their public key using the formulas. For Alice, YA equal to alpha to the power XA mod q. After substituting the value, Alice will get his public key as 8. Similarly, Bob will also calculate his public key using the formula YB equal to alpha to the power X. After computing the public key, Alice and Bob will share their public key with each other. After the key exchange, both will compute the secret key. Alice will compute the secret key using the formula Z equal to YB to the power XA mod Q, and Bob will compute the secret key using the formula Z equal to YA to the power XB mod Q, and both will get the same value 2 as their secret key.
Now, I will explain the man in the middle attack. In this attack, a third person named Dart intercepts the communication between Alice and Bob. When Alice sends her public key, Dart captures it and sends her own fake key to Bob. Similarly, Dart sends another fake key to Alice instead of Bob's key. So, both Alice and Bob think they are communicating with each other, but actually they are communicating with Dart. Dart creates two separate keys, first one with Alice and another one with Bob. In our program output, we can see that Alice and Bob generates different keys, while Dart successfully generates both the keys. This means the communication is compressed and not secure.
Now I will explain how we detect attack in our implementation. First we compare secret keys generated by Alice and Bob. Then if the secret keys are not equal, it indicates a possible man-in-middle attack. The program will display an alert message when such a mismatch occurs. This is a basic method to detect the attack. In real-world system, the stronger methods like digital signature and certificates are used to detect the attacker and prevent the attack. From this experiment, we conclude that Diffie-Hellman is an effective method for secure key exchange, but it is also vulnerable to man-in-the-middle attack authentication. Therefore, combining secure key exchange and authentication is necessary to complete the security.
Finally, we implemented Diffie-Hellman using Python. In the normal case, Alice and Bob generate the same shared secret key, ensuring secure communication. We then simulated a man-in-the-middle attack where an attacker sends fake keys. This causes Alice and Bob to generate different keys while the attacker gets